Hello everyone. In this video we are going to talk about 3D static structural simulations, and this video will include several different items regarding finite element in ANSYS. So let's get started. Here we go to the design modeler and we are going to create an L-beam basically. And then we are going to apply static load on it. So here, first I go to the XY plane and I create a sketch. I change my units to mils before I do anything. And if you want, you can always turn on the grid. And here, the way I'm going to create the L-beam is by using cut extrude, because I wanted to show you this command. So here I draw a rectangle and provide dimensions to it. So I make it 100 by 50. Zoom to fit. And then I use the constraint tool in symmetry and make sure the two sides are symmetric like this, and then I do the same thing for the x-axis. So like this, and then this one. Okay, so now it's all symmetric. Now I can extrude it for 400 mils, right? And then say generate. So here I got this. Now I want to show you cut extrude. So I go onto this plane. I click on this plane and I see normal to it. And then I create sketch number 3 or 2. It doesn't, the numbering is based on how many you have made already. And here I make another rectangle like this and provide dimensions for this guy. So make this one 80 and this side 40, and use the symmetry as well. Make sure this drawing selection. Make sure this one, and this one has symmetry. There we go. So now, look, I go to extrude, but this time instead of operation add material, I say operation cut material. Use the same 400 and generate, and there we go. Right? So the extrusion also involves cut extrude if I change my operation from add material to cut material. And I also want to apply some fillets to this internal edges to avoid its stress concentration. So I go to fix radius fillet under blend, and then I choose this edge and rotate it and hold down and select this edge. Make this 10 mils, and then I apply and generate, and there we go. Right, so now if you look, you have your fillets and your object is ready to go. So this is one way to create 3D objects, is in the modeler. Here I did it extrude or cut extrude. The other way you can do it is if you go into, let's say, SolidWorks, right? So here I made the same object with the same dimensions. So another way that you can do it is you can go here, and instead of bringing it from design modeler, you can right click and say I want to replace it, and then browse what for basically a file that you exported from SolidWorks. Now most of the times ANSYS reads the files directly from SolidWorks, so when you're searching for your file and browsing for your file, you should be able to directly bring SLDPRT file, but sometimes it doesn't. My suggestion is, if you want to export, and make sure you always can bring it into ANSYS directly instead of SLDPRT or instead of STL files, which I absolutely suggest not to use because STL is just the external geometry. I suggest that you save it as a step file. So go here and basically save it as a step file, STEP. And then here you can definitely go ahead and bring it. Another thing that you have to keep in mind is even if I'm here applying material in SolidWorks to the object, when I bring it here as a step file, the material is not being transferred to ANSYS. So you have to apply the material to your SolidWorks step file once you bring it into ANSYS. So here I have that guy as L-beam step, so I can bring it that way, right? So the analysis type here, you make sure it's 3D, not 2D. And once you have the geometry, now you can double click and go to model. Okay, so here we are in 3D. We can first generate a mesh. And if the mesh is not appropriate, we can always change it. So here is relatively good, except maybe these areas you need to resize it. So I can go ahead and create sizing now for 3D. I'll discuss later in one of my future videos about meshing, but in general, these hex elements, which are basically like a prism, they are way better and faster compared to tetrahedral elements. Okay, so these are good if they are possible. And we'll talk about multi-zone and everything, but right now, let's see here, I select the whole object, and then instead of 20, I make it maybe 5. And the other thing I want to do is go ahead and do a refinement along, let's see if it allows me to select the surface. If not, I can do edge. So align these edges close to these edges if I can have refinement, and hopefully this is going to give me better mesh. So here now you see it's mostly done using tetrahedrals, but they are much smaller, especially in these areas of concentration of stress. So this is good, maybe too fine for the purpose that I have. So you can always go ahead and change the sizing and update the mesh, right? But always make sure your mesh is relatively fine enough, and we'll talk about it, the metrics for the mesh. So let's say this is the object that I have. Now, if we go here, and let me show you the weak spring that I mentioned one time. So here I'm gonna go ahead and apply a force on both ends. So apply a force here on this face, and the force I applied as like 5,000 newtons, right? And then I go to the other side and apply something similar. On this face, and this magnitude I make it negative 5,000 and apply to that surface. So let's see if it makes any sense. And here it says click a direction. So you see this force here is inward, that force here is the same. So I need to change that then to positive 5. There we go. So now if you look, the two forces, if you look closer, the two forces, this one is basically in the positive z direction, and this one is in the negative z direction, okay? So the object is statically in equilibrium, right? And if I want, let's say, just to look at the total deformation and say run it for me, what do you think would happen? The object is at equilibrium, and it is in basically tension, so it should work fine, but look at what happens. So if I run this, it is going to say, hey, there is not enough constraints and the object might have a rigid body. And you might say, well, the objects should be at equilibrium, but guess what? This is a numerical method. It's not perfectly accurate. in the two sides of the equations for nodal displacement, k times x equal f, you never get both sides to be perfectly equal. They are approximately equal. There is always residual displacement or residual force, and the object is not going to be perfectly at equilibrium. So if you do not constrain the object and do not constrain the degrees of freedom, and just say because of the balances of the forces, the object is in equilibrium, guess what? It is going to pick on you, and it is not going to give you any result, as you can see here with these reds. There is definitely a problem, and the object is physically moving, so it cannot calculate for you what you want. So in those cases, what you want to do is go under this analysis setting and turn this guy weak springs off, turn it on. What this one does, if the object is not perfectly constrained and might be subjected to some rigid body motions because of those residual terms, although all the forces would balance each other out, this guy will take care of that rigid body motion and kind of basically neglect it. So if you turn that on and run it one more time, hopefully this time might give you a warning like this, but it should give you some results this time. And as you can see, right, it is going through, not like last time, and you see that there is some results here. So it's by no means really suggested to leave the object like that without proper constraints, but if there is any suspicion of that, turning on those weak springs can overcome the problem. So what I'm going to do today is that force is good. I'm going to get rid of this force, and instead of this force, I'm going to apply a fixed geometry, fixed support here, so to make sure all degrees of freedom are gone. So now I'm in a good shape to basically do a proper static analysis because there is no degree of freedom left. But what I would do is, let me add the stress here as well. What I want to show you is some other types of load other than force. I want to show you some other types of loads. But we want to make sure here we are staying within the linear region. And we are not going to go to the plastic deformations. So the yield strength for structural steel, which is the material right now, is 210 meg. So as long as the maximum here is below that, which clearly it is way below that 4, I am safe, relatively safe. Okay, so it's nothing big. But what I want to show you is this. So I go here and insert, and this time I want to show you other types of loads called inertial load. One of them is the standard gravity, Earth gravity. When you add that by default, it is in negative z direction, but here your downward direction is negative y. So go ahead and change it to what? To negative y direction. Okay, always make sure that the direction of that is correct. The other thing you can add is accelerations and inertial forces. So here, if you give it acceleration in any direction, the equivalent force for that acceleration is going to be in the opposite direction. What does that mean? It means, let's say here, if I apply an acceleration in the x direction, right, let's say 100 or something like that, the equivalent force is backwards, and that is because of the equation F equal ma. If you bring the inertial term ma to the left side, it will be negative ma. It's going to be F minus ma. That's why a positive A is equivalent to a negative inertial force of negative ma. So just keep in mind, if you want a force in the negative x direction, your acceleration should be in the positive x direction, and so on. So here I can apply those two as well, and then I can solve again. So these are two other types of loads, gravity and acceleration or inertial forces, which you can apply. And you can again look at the deformations, you can look at the equivalent stress or anything for that matter. Now they are not big for big objects, right? But you can see that as well here. Okay, so now you have several you have several directions of displacement, right? You clearly see the object is basically moving in X and Y direction. And now if I go back and get rid of these, I want to show you some other types of forces, as I said, or loadings. The other thing you can apply is a pressure, right? So let me show you a pressure. So here I click on pressure and I apply the pressure here. Now, of course, it's going to be a uniform pressure, right? So I can make it a uniform pressure of as many megapascals that I want. So let's say 2 megapascal, right, on that surface. And here apply to this, and then go ahead and solve, right? So this is the result, and clearly you see that the maximum stress is way more than the yield strength. So now we are in plastic region, and large deformations are possible. So if large deformations are possible, ideally, as we'll discuss later in one of our future videos, you have to go here and then turn on these large deformations. That is off. You have to go ahead and turn it on, because you might be subjected to what large deformations. You see your maximum deformation is 3 mil. Now, with about the dimensions of 100 by 50 by 400 mil, 3 mil might be considered large, might not. It depends on your application, but it isn't clearly, with respect to most other static applications, 3 mil could be a big number. So you might need to turn that large deformations on, as I said. But here I'm gonna reduce the load, okay, because I don't want to go in the plastic region. So instead of 2 meg, I might make it half a meg or something like that, so I can stay below the yield strength. And here my total stress is 133, below 210. Another question that you can ask me is, here I deleted this pressure that was uniform, that could I apply a pressure that changes along the length of this beam, like along the Z direction? Can I have a variable load, right, with direction? And the answer is yes. So here, if I go and apply a pressure on this surface, how can I make it variable? So here, this magnitude, right, that you can see, instead of typing a number for it, I say I want it tabular. And then I scroll down, and here it says independent variable, and then instead of time I make it along the z-axis. And here I get this table on this side that says at 0, which is over there, I have some pressure, and then it keeps going up into this other direction. So let's say at 0, which is there, that is your free end of the beam. You want your maximum load, and then you linearly want to bring it down until this fixed end of the beam, which is at 400 mil, and you want to bring it down to 0. So you want, let's say, a linearly increasing load. So you say at 0, it's, let's say, half a megapascal. At, let's say, 100, it is, let's say, 35. At 200 it is 0.25. At 300 it is 0.1, and then at 400 it is 0. Now this is clearly not linear, right? Because you have to go from 0.5 to 0 in a linear fashion. So this is completely tabular data, and definitely not a linear pattern. Because if you wanted, you had to go by steps, right? So for example, you can go 0.3, 0.4, 0.2, 0.3, and 0.4. Now this is a linear pattern, right? But you can change it. The good thing is, with tabular data, you can change it to be any function that you want, and you can insert as many points as you want, so you can create a completely arbitrary function for the pressure. So now this is going to be your variable load. As you can see, in the red areas you have maximum pressure, in the blue areas you have minimum pressure, and now you can solve basically with this one. So this is the plot for that pressure, right? As I said, by adding more points and more data, you can create any function that you want. And this is the stress for it, right? And the total deformation. One other question you might ask is, can I make the load to be variable with time? Like, for example, can I gradually increase my load, or can I unload the object, right? So, for example, if you are on the stress-strain curve, right, as you increase the load and you move in the linear region, then you might move into plastic region and so on. Can I do such a thing in ANSYS? Can I increase the load? And the answer is sure, you can. So let me show you that one. So, for example, here, let's say I want to increase the load, right? Not in steps like this, but with time. So the independent variable is going to be t for the load, not z. So how can I do that one? So here I go ahead and maybe I use the same pressure. So I apply it here. And before I do that, I need to go to the analysis setting and change the number of steps. And this number of steps is the number of points in time that you want to apply your load. So let's say you want to go from 0 to maybe 1 megapascal or something like that. And you want to do this in 10 steps. So here you say the number of steps is 10. And so this pressure that I'm going to apply, I'm going to, you see here, this magnitude, I'm going to do it with this tabular data here versus time. So at time 0, I'm at 0 megapascal, and then keep increasing, right? You can just double click on this data and change them, and then keep going up at different time points, right? I keep changing my pressures until I get to the final pressure, right? So here your independent variable is going to be time. Here we go. So now you see this is how pressure is changing versus time, and you're increasing the load in a linear manner with time. So now let's go ahead and solve it again. And we can clearly see in the deformations or in the stress that not maybe in the animations, but if we create a plot of stress versus strain of 1 point, you clearly see that the stress is increasing. And that's my next topic, which is adding a chart or a graph. So let me show you that one once the data is available. So here is the stress, and if I show it to you, you clearly see that, right? Look at the time, it is going up, and then what? It's increasing, right? But it might not be super clear, right? You see that over time from 0 to 10, the stress is increasing. But the best way that you can do it is by basically plotting the stress versus strain of one specific point. That can show you that graph that you always see in solid mechanics. So if I, let's say, go to a point of maximum stress, which is apparently this corner here, right? I want to plot the stress versus strain for that corner, that node basically here. So how do I do that? I want to create a custom chart. So in order to do that, I go to the solution, I insert, and I'm not going to go to probe. I'm going to go to stress. I'm going to go to the equivalent stress, and I can rename it and call it equivalent stress at vertex, right? And then I can go ahead and do a similar thing for strain this time. And again, I can call it equivalent strain of vertex, right? And I need to define these at the location that I wanted. So here I turn my option on. Here I can choose the point, or I can choose it on the mesh. And here when it says geometry selection, instead of all body, I'm gonna go ahead and select that node and say apply. And the same thing for here. Again, instead of the whole thing, I'm gonna select the very same point and apply. Right, so now these two results are going to be the stress and the strain maximum at that location versus time as the pressure goes up from 0 to 1 megapascal. And I can retrieve those results individually. I don't need to rerun the whole thing or resolve the whole thing, right? So this retrieve this is going to save you a lot of time. So this is the stress, and this is the strain. And seems like the stress is not changing while the stress does change. So let's see. If I look at my stress data, you see there is a minimum, there is average, and no, the data is actually changing. So here I grab these two, I hold down control and grab them and go to chart. And for x-axis, instead of choosing time, I choose my strain maximum. And then I come down here and double click on display time to turn it off or omit it basically. And then I don't want the minimum results, so I double click on them and turn them off as well. So now this is going to be the graph that I talked to you about. As you clearly see on my x-axis, I have millimeter over millimeter, which is a strain, and I have megapascal, which is what? Stress. Actually, it goes from 26 to 266, so it's like a factor of 10. Yeah, that's the reason I thought that it's not changing. It is changing, but it's by a factor of 10, so that's why I didn't see it. And clearly here you see that it is increasing, right? And after probably 210 or so, after here, you are gently starting to go into the plastic region, right? So the question is, can I unload? Can I load and unload, right? Can I decrease my load? Absolutely. The same way that you did this pressure, remember you went to 0.5 and increased it to 1. If you want, you can decrease it gradually and go back to what? Go back to 0. So 0.3, 0.4, 0.3, or let's say if this is 0, can go 0.1, 0.2, 0.3, 0.4, and you clearly see that here I'm loading and unloading. So go up to 0.5 and then gradually come back the same way to 0, right? So now I can do the same thing here. And here is the result of the maximum stress that you clearly can see. It goes up and then goes back down to 0, right? So loading and unloading, and your chart clearly goes to 133 and then comes back in the linear region back to itself. Okay, because you're not exceeding the yield strength. So this is this part. There is one extra part that I need to tell you about, and that is adding frozen versus adding material. So let me show you that one, which is related to the geometry. So here is that L-beam that we made in the beginning, and now this is what I want to do. I'm going to apply some patch somewhere, and let's say I use that patch as basically another material on which I'm going to apply my force. So here, as I said, I want to add a small plate on the top of the top surface of the beam and use that as somewhere that I apply the load of another object. So here I really want to create a second object, and let's say the material for this small plate is different from the material of the beam. So I have welded two different metals together here. So what do? Here I choose this plate or surface, and I go to sketch, and I use the rectangle tool, and let's say here I am creating a rectangle like this and give it some dimension, let's say 40 mils, and then here I go ahead and extrude it for some small amount, maybe 5 mils or something like that, and generate it, and let's see it. So now, if instead of adding material, I go ahead and say what? Add frozen. What does that mean? Means this piece is different from the rest of the beam. This is a new object. This is not going to be merged with the rest of the beam. If I say add material, they will be merged as one object. You see right now I only have one part, one body, but if I say add frozen and I generate that, first of all, you see the colors are different. Second of all, you see I have two bodies, solid 1 and solid 2. So I can apply different materials to them even if I want to, right? So here you see I applied that extra patch there by adding frozen, and now I go ahead and apply different material to them and apply the force on that top plate and then do the structural analysis. So here you clearly can see that I have this separate patch and it's under geometry, and right now both of them are made of structural steel, but if you don't like this one to be structural steel, go ahead here under assignment and you can add different material, right? So if you know your material, you can type it here. Let's say I want this to be stainless steel, right? Or anything else, or copper or something else. So if you can find your material here, let's see if I can find something, or aluminum, let's say copper alloy, for example, something like that. So now that is a different material, as you can see. And the other thing that you have to pay attention to is now there is connection. If you go under connection and contact, you have a contact region, and the type of contact that you have here is called bonded. You can change it to no separation, frictionless, rough, frictional, and so on. And what is the difference here? Well, frictionless, frictional, and rough are kind of easy to understand. What is bonded? What is no separation? Bonded means the surfaces that are in common between the two objects, this small surface patch here, there is going to be no degree of freedom between the nodes of the two objects. There will be no penetration between the nodes, and the nodes cannot move with respect to each other, right? They are completely like glued together. If I say no separation, what does that mean? It means in the vertical to the surface direction, which is in this case in the y direction, you cannot separate the objects. In the y direction, the displacements of the nodes of object 1 and object 2 are going to be the same in the contact area, while in the tangent directions, which is x or z, they can slide. Okay, so no separation comes with tangent slide, degree of freedoms, but bonded means there is no relative motion between them whatsoever. So let's keep it that way. Let's assume that they are welded together, right? And then I'm going to generate some mesh for them, and then I'm going to apply some force, and I can basically look at the stress or other deformations in them. But first, remember, we have to apply constraint as well. So here we apply the force. Let's apply some fixed support, let's say on this end. And now I should be good to perform the analysis. So let's go ahead and solve. And here clearly you have two objects, and the stress is not going to be perfectly continuous, as you can see here. As you move from one object to the other, the distribution of the stress is also quite a bit different in the material, or at least the limits, I would say. So here you clearly see that I have two solids, and I can look at the stress in both objects. I can look at the stress in one object, right? When you do this, instead of all bodies, I can look at one body or any area that I would like to look at. So I just wanted to tell you about this add frozen feature, that you can add separate objects and then have them bonded together, or have them frictional contact with frictionless contact, no separation contact, and so on. So if you have, let's say, the teeth of gears on the top of each other, or you have the bolt and nuts that are having contact with each other, you can go ahead and create their geometries using add frozen method and bring them here and apply your constraints and loads and so on. So this add frozen is to create more than one object and more than one material assignment. So hopefully this video was useful to you and I could transfer to you some relevant material. I will see you in my next video. Thank you so much.